Kia ora everyone, my name is Andrew Lewis and as you see there, I'm a team leader here at Callaghan Innovation, which is on the wider site. Some of you may be going on the tour later to come to visit one of my labs, so that'll be good. I'm also responsible for the magnetic resonance facility on site. It's the nuclear magnetic resonance. It's nuclear because it's measuring properties of the atoms, not because it's radioactive. Okay, hence we call it MRI at the hospital, magnetic resonance imaging. You might be familiar with that. Anyway, I'll get going and we'll see. So basically, what I'm going to talk about today is some of the ways we can actually check the labeling on food, right? A lot of things we buy and eat and consume, you know, we're trusting the label. What we're buying is what the label says. How do you check those things? We're probably familiar and pretty good at measuring things like the sugar content and the salt content and all those things. But what about when it says it's from New Zealand, or in the case of wine, it's a Pinot Noir? How are you going to measure that? How are you going to verify it? So what I'm going to talk about today is one of the ways we've got in New Zealand now to do that, and what we're doing to, why we're doing that sort of stuff. First of all, what is nuclear magnetic resonance? It's using the nuclei of the atoms inside a big magnetic field to measure the properties of the compounds, atoms, ions, molecules inside the sample. The sample can be a liquid or a solid, but we usually dissolve the solid, if it's not a liquid, into a suitable solvent. We then put the sample into the middle of the big magnet here, and we use some radio frequency electronics to measure the signals. In an MRI, your body or you are the sample, and what we measure there is all the water in the different tissues of your body, like the bones, your eyes, you know, the water in your eyes, the muscles, the fat, and that's why you get a picture that looks like black and white photo. The main applications for NMR are quite different than MRI. We, as chemists, we use it to determine this molecular structure. So if somebody makes something in the lab, how do they know what they made? They put it in one of my machines in the lab, and they measure the properties of it, and they can tell exactly what atoms are in there and how they're joined together. So that we also use that to discover things out of plants. If we take something to find a new medicine, for example, from a plant, we might keep extracting the plant and try and find a special thing in there that makes it a medicine. We can use that to determine what the structure is when we don't know what it is to start with. So we can also use it for identification. You give me a white powder, I can tell you what it is. Quantification, one of the really good things about magnetic resonance is it's like a balance. I can tell you how many atoms are in the sample of each type. So I can use it to check weighing or to do that and tell you how much sugar is in the wine or how much protein is in the milk, things like that. What I'm going to also talk about today is the next step, which is to do with the origin and things like that. And that's how we can use it to classify or screen samples to check their claims on the labels. Now, lots of advantage of NMR. People don't really understand this. It is the most sophisticated instrument we have for chemists. It measures, I know how to do typically several hundred experiments on a given sample. So unlike most instruments we have in the lab, they do one or two different measurements. NMRs do thousands, and we can program more all the time. They do it on the same experiment on different atoms or nuclei in the periodic table, or we can do combinations. So there's a really high number of experiments we can do. It's intrinsically quantitative. We can basically check a weighing experiment with it. So there's not many techniques we have that are like that we can trust to give us a value when you read a number that it's trustworthy. It's highly reproducible. My machine will give you the same result as another one in my lab, or one in Germany, or one in France. So without that, we couldn't do the next step, which is the classification. We're getting a fingerprint, and everyone can get the same fingerprint if they run the same sample. Okay? It's also non-destructive. For some things, you get your sample back. That's really useful if you've only got a tiny amount of it, or only one sample. So you've got one fraudulent sample. After you measure it, you don't want it destroyed because maybe you have to do some other measurements. What you get is a radio frequency spectrum here, which looks like a whole lot of peaks with a scale on the bottom. Here we've got 30 replicate samples prepared by 6 different people. run on 3 different spectrometers around the world. And you can see the reproducibility is very high. That's basically our fingerprinting aspect. So we can be sure if I run it or you run it or another lab runs it, we're going to get the same fingerprint, so we can be sure about the results. But there's a lot of other advantages too. I'll just tick off a few there. The ability to use multiple different nuclei, so we can use hydrogen, carbon, phosphorus, silicon, sodium, oxygen, pretty much everything on a periodic table. We can easily change the measurement we do between each sample. So we don't have to calibrate the instrument for one day to measure wine, and then next day calibrate it again to do honey. I can put a honey sample on, a wine sample, a chemical to measure, and just queue them up. Right, that's really helpful. It does targeted and non-targeted. What does that mean? If I want to detect, can I measure sugar in wine? I can just set up a measurement to measure sugar. But I can also just measure the spectrum of the wine and go, is there anything in there that I didn't know about? The biggest fraud thing we're probably common knowledge in New Zealand would be the melamine in the milk powder. So on NMR, that shows up. As soon as you ran it, you would have said, hey, what's that stuff in there? There's something that shouldn't be in there. And we would have been able to tell what it was. But no one ever ran that experiment, so they didn't know. Another great thing about it is I can measure the spectrum, and later on I can go, oh, I wonder if any of that chemical was in there. And you can go and look. You don't have to go back and run another sample. You already have the data. So that's pretty useful. What kind of food is adulterated? Oh my God, it's so terrible. Sometimes I can't buy things at the supermarket anymore. This is the list of top 12. And I'd say most of you eat those things regularly. Okay. How would you even know? Now, most of the adulteration is not going to kill you. It's not like the melamine in milk, right? Instead of getting olive oil, you might get hazelnut oil. Instead of getting wine, you might get some water with some alcohol and some color and some flavor, right? Maple syrup, probably just sugar syrup, unless it's really maple syrup, right? Apple juice, you think, who would bother? Herbs and spices. We just had some of those today. In Australia, the herb thyme, you buy it, less than, even the premium brand, less than 50% of what's in the jar is actually thyme. The rest of it is olive leaves. Right? It looks the same. Tastes the same once it's been in the jar, but it's not. Okay? Eggs, is it free range? How would you know? What test would you do to know an egg is free range or not? Can anybody tell me?
I can have it from out of my chocolate pen.
That's right. Yeah, exactly. But if you're buying the supermarket, do you think I could tell the difference between a free range egg and a non-free range egg?
Read on the box, it says free range.
But it is actually possible. And in Europe, they have institutes the size of Callaghan here, 300 scientists, 47 labs like that in Europe. All they do is test this food. We don't do anything like that in New Zealand. It's crazy. Lots of things we can say, you know, is it free range, GMO, extra virgin oil, Manuka honey, classic. For wines, I think that can tell the geographical origin, purity of things, mislabeling, so I can determine all those sorts of things. So NMR is able to do all of these things, which is pretty powerful, right? Without much effort. Basically, you need to make some sort of database and some validation things, and then you can measure these things. The other reason I'm interested in it, which is why I got the machine I got, is it's about protecting our brand image. We are seen overseas as a premium supplier of high quality food. We're trustworthy, all of those things. Anything you see here, we can sell for a premium price because it comes from New Zealand. When I went to Germany and Europe last year, I went around and bought New Zealand wine. Everyone's saying, why are you buying New Zealand wine? You're in Europe, right? I was bringing it home to see if it was real. So I brought home all the New Zealand wine, honey I could find. Test it. Not all of it. Okay, kiwi fruit. Can you tell if the kiwi fruit's from New Zealand or was it grown in China? We're working on things to do that. There's lots of scandals around, so you probably heard about that one. There's winemaker, you know, we exported hundreds of litres or thousands of litres of wine that had sugar added. Not good. So I have an NMR food screener. This is a specified model that is now 82 of them around the world. And all those countries that have got them have been building up a global database of their wines, their honeys, whatever they want to put in there. And what's happening now in the last year or two, the import restrictions are happening. So as part of your import requirement, they're going to test it on these machines and make sure it really is honey from New Zealand or wine from Spain, olive oil, whatever. Otherwise, it won't get in. So that's really important for us. So we need to test it here before it goes there to make sure it's good. The company I'm working with is called Brooker, and they make the instruments we use. They've been doing this for a long time, and I apologize, this is European, so it's got a decimal point instead of a comma. But they measured 28,000 fruit juices, 19,000 wines, and 10,000 honeys. That was a few years ago, so it's actually higher than that now. And they've developed amazing methods. So we have 50 models for different sorts of fruit juice. I can tell if water's been added to the fruit juice, if it's ever been frozen, is it made from concentrate? Is it really an orange from Slovenia, or is it from, Yugoslavia? You can tell, and it's really amazing. At the same time, I can measure lots and lots of values of compounds inside. So the numbers in the middle there, and fruit juice, I can tell you from a single measurement, not only where it came from, but 40 compounds in there, how much of each of those, sugar, amino acids, all of that, from a single measurement that takes a few minutes. So it's very powerful. Without having a database before you start, so that all works. And when we've collected wines for years and we've run them through, what happens if you want to know, I shipped 10,000 litres of wine, what did you get on the other side? So that's very simple, because we can just do a direct comparison of the fingerprints. So I only need 2 samples for that, don't need any databases, and I can tell from the features that we see in the spectrometer. You can get very detailed. You can look for very small changes. Did the product change during the shipping? Did it get too hot on the voyage across the Pacific Ocean? Did someone dilute it by 10% with water before it got to the consumer? Those are the sorts of things we can tell. And that measurement takes about 20 minutes. More importantly, the things I thought about doing first was the wine, because there was a wine fraud going on. We basically take the wine, we add 10% of a buffer, which has basically got to balance the pH, and then we actually adjust the pH very precisely. We then suppress the biggest signals in wine are from water, which is about 80%, and ethanol, which is 10 or 15%. And then we can see all the small compounds in between. We see hundreds of compounds in there, and we can do some very sophisticated analysis. Here's a spectrum of wine, a part of it. You can see I've suppressed some signals here, but all of these compounds here are known compounds. Tartaric acid, you probably know. Methanol, there is some methanol in wine. Lactic acid, acetic acid is vinegar. But once we suppress it, we can also blow this up, and we can see hundreds of more compounds in here, which we can analyze. Sorry about that. Yeah, so that's what we do. It's basically creating a fingerprint. As I said, we can measure and quantify lots of compounds per analysis there. So on the list here, you can see the first page of about a 5-page report that indicates how much of each compound was there, whether it's above the European standard level or above something. The little graphs at the right-hand side indicate the range that's common in, let's say, white wine. And the bar indicates what the measured value was for that wine. So there's a lot of information here. The green spots there indicate that those levels pass the regulatory levels. It's also some calculated things in there, like the carbohydrate values and things like that, that the chemists are used to, or winemakers need to use. What's really important though, lots of techniques can do that, that's easy, is this kind of classification. So I can say, I've run a wine, is it a Pinot Noir? And it has about, I don't know, 80 different grape varieties in them at the moment. And you can see it comes back with a statistical model where the black star is there. And that's showing that it was some very unknown, uncommon wine variety to me, a grape variety, but it's very clear what it was and that it's not the other ones. I don't know very many methods that can do that, but we can, from the same data, we can test also the geographical origin, country of origin, or in France, it even goes down to the individual vineyards in some cases. And we can even tell what year the wine was made. It's amazing to me, all from that same measurement. We can do the same thing on the juices. I haven't done it here, but this was apple juice problem. So they wanted to know which country it came from. And in China, for example, there was lots of fraud going on. They can tell from which region and in some cases which orchard it came from, which is pretty amazing. We're hacking this method basically for the yellow kiwi fruit to prove that kiwi fruit sold around the world are from New Zealand or from China or from Chile. And at the moment we can tell regions within New Zealand where they're grown. Not quite down to vineyards, but we're all orchards, but we're going there. The other one is honey, New Zealand Manuka honey. There is, depending who you listen to, 6 to 10 times more Manuka honey sold than we make. Where did it come from? So we're building a model. I've already run about 600 honey samples at the moment, and we're doing all the other varieties of honey too, not just Manuka, Rewa, Pahutakawa, all the other ones. And at the moment, there is a model for New Zealand and Manuka and even Kanuka honey, but we're trying to improve that. I've been working on this since, well, this is 2015, so nearly 9 years now. So it's not a fast project, but when it's done, it's really powerful. Yeah, those models exist for lots of other honeys too, acacia honeys, chestnut honey, all the kind of expensive honeys. It does very sophisticated analysis, so I won't get into the details, but there's single variant models and double, it's not just one test you do multiple tests. So what we're trying to do here is not actually prove the veracity of the product. We're trying to screen it and go, hey, this product looks suspicious. Let's take it and do some proper testing. But it's a very fast way to screen for those bad ones. He's just showing the new models kind of does, rather than everything or not, we're just asking, is it Manuka or not? Okay, so it's very clear, and we get some nice statistics for the people that like statistics at the bottom, showing how reliable that conclusion is. The other thing my team does, which is a world leading to, we're the only lab in the Southern Hemisphere doing this. We measure all of the ingredients and things that go into infant formula for the phospholipids that are used for the baby's brain development. So we get the raw materials, but we also get the final formula to make sure that they actually got into the product. We measure a phosphorus spectrum in this case, and we can quantify, I don't know, about 15 different compounds in there and make sure that they're in the right ratios to make sure that those products are safe. It's also measured in a lot of the health supplements that people might take, the omega-3 oils and things like that. A lot of them now have phospholipids in, and we want to measure that, so we can do that too. But as I said, there's only one other lab I know of in the world that does this, so we're pretty specialized. We did not stop in COVID. My team worked entirely right through because the milk production is still going on, and so we had to keep measuring that. Infant food is very important, and yeah, that was a lot of work when there's no one else on site, and we're coming in every day to make sure that's keep going on. And that's all. Thank you very much for your attention.